Doing mathematics means, above all, proving what one claims. We have seen that the stereographic projection sends circles on the sphere, not going through the pole, to circles in the plane. And now we are going to prove it. Even though this has been known for many centuries, it is I, Bernhard Riemann, who will present this proof to you. I am frequently honoured since one speaks today of the Riemann sphere. Proving is much more than showing. It is not enough to see in a movie that some curve looks like a circle, to be sure that it is indeed a circle. A mathematical proof must use reasoning to be convincing, and has to explain why it is indeed a circle. The great Euclid, during the 3rd century before Christ, formulated the rules of the mathematical game in his book, The Elements. A proof has to rely on facts that themselves have to be proved. But one has to start with something, so that some statements have to be accepted without proof. These are the axioms. Therefore, mathematics appears as a gigantic construction, whose foundations consist of the axioms, and such that each brick rests on the previous one. In order to prove the theorem about the stereographic projection of circles, we should, in principle, start with the axioms. Of course, we have no time for that now. We will assume that we already know the theorems of geometry which are studied, say, in secondary school, and we will prove this theorem. Start with something simple: the intersection of a sphere and a plane. We see that if a plane cuts a sphere, and if it is not tangent to the sphere, then the intersection is a circle. We can see it, but why is it true? How do we prove it? Well, let's consider an arbitrary plane, coloured in blue. We can draw the perpendicular from the centre C of the sphere to the plane. Let's call P the foot of this perpendicular. Consider 2 points A and B on the intersection of the sphere and the plane. And let's look at the 2 triangles CPA and CPB. They share a common side, CP. Both have a right angle, since the angle at P is of course a right angle, since the plane is perpendicular to CP. But note that the hypotenuses AC and BC have the same length because A and B are on the sphere, and are hence at the same distance from the centre C. But remember Pythagoras' theorem. Since our 2 right-angled triangles have 2 sides of the same length, their 3 sides must have the same length. Hence, we have proved that PA and PB have the same length. That is, that A and B are on the same circle with centre P, in the blue plane. Therefore, we have proved that all points which are both on the sphere and the plane belong to some circle. Does that imply that all points on this circle are on the sphere and on the plane? A priori, no. We still have to prove it. Let A be a point which is on the sphere and the plane. Consider the circle in the blue plane with centre P and that goes through A. We will prove that this circle is contained in the sphere. Let B be some point on this circle. Look at the two triangles CPA and CPB. They share a side, CP. Both are right-angled triangles since the angle at P is a right angle. But the lengths of PA and PB are equal, since A and B are on the same circle with centre P. Again, using Pythagoras' theorem, we conclude that the hypotenuses have the same lengths. CA equals CB. This means that the point B also lies on the sphere, since it is at the same distance from C as A. That's it. We have proved that when a plane cuts a sphere, the cross-section is a circle. Now let's look at a diameter APB of our circle. And let's place it in the plane of the screen. The blue planes appear as a straight line on the screen, and the sphere appears as a circle. Let's draw the tangents to the circle at A and B. They intersect in a point S. Of course, the line CS is again a symmetry axis for our figure. Why? Well, because the triangles CAS and CBS are equal. Why? Because they are both right-angled triangles having a common hypotenuse, and the sides CA and CB have the same length. Why? Well, because these are two radii, of course. You see, if we had to go right to the end of all the arguments, this movie would be the longest in the history of the cinema. Look, we have just proved that any circle drawn on a sphere can always be thought of as the contact locus between a cone of revolution and a tangent sphere. If you like, the sphere is like ice cream in a cone. Well, we mustn't forget what our aim is: to show that the stereographic projection carries circles onto circles. Let's first prove what mathematicians call a lemma. Here is the tangent plane to the sphere at some point A, seen from the side. Now here is the tangent plane at some other point B, also seen from the side. These two planes intersect on a line D, but at present we only see one point, since this line is perpendicular to the screen. The figure that you are looking at is symmetric with respect to the bisecting line of the two lines that we see. This three-dimensional picture is symmetric with respect to the bisecting plane of the two tangent planes. Choose some plane containing the segment AB. It intersects the line D in a point M, unless it is parallel to D, of course. The symmetry of the figure with respect to the bisecting plane shows that AM and BM have the same length. The triangle ABM is isosceles. Here it is. That was our lemma. Well, now we can prove our theorem using what we have just learnt. Consider a circle on the sphere which does not go through the North Pole. We want to show that its projection is a circle. Look, if instead of projecting onto the tangent plane to the South Pole, we projected onto some other parallel plane, the famous theorem of Thales would imply that all the projections are similar. Hence, in order to prove our theorem, we may choose the projection plane as we wish. of course as long as it is parallel to the tangent plane to the South Pole. Well, let's place our yellow circle in a cone. Remember? The ball of ice cream in a cone with vertex S. Well, we're going to project onto the horizontal plane through S. The point B projects onto a point D. But look at the figure. The triangles AMB and DSB are similar. Why? Well, again, Thales' theorem. Do you agree? Now, remember our lemma. The triangle ABM is isosceles. Hence the same is true for the triangle BDS, so that BS has the same length as DS. When B moves along the yellow circle, the segment BS keeps tangent to the sphere. Its length is therefore constant. Since BS and DS have the same length, the moving segment DS also retains a constant length. Let's see. Saying that DS has a constant length means precisely that D describes a circle with centre S, so that the projection of our yellow circle on the horizontal plane through S is contained in a circle. We have seen that, by Thales' theorem, this implies that the projection onto the tangent plane to the South Pole is also contained in a circle. QED, quod erat demonstrandum.